Okay, so as Megan said, I am at IPAC. So I'm going to start by saying what IPAC is, because often people don't know, although here at CCA, you guys are in a unique position of being similarly confusing, I'm sure, to outside people. IPAC is a science and data analysis center on the Caltech campus. It started as an offshoot of JPL in the 70s, specifically to get all of the public data archives out from behind the JPL firewall. It was a pain to get data up to JPL, and it was a pain to get data away. And they were like, this is silly. It's public data. So we are a science and data analysis center on the Caltech campus. We do a bunch of things. We are a NASA Science Center, so we ran the Spitzer mission. We're running other missions. We do data processing and archiving for a bunch of missions. And a bunch of archives. So the NASA Exoplanet Archive is there. The NASA Extragalactic Database is there. The Infrared Science Archive is there. We're helping develop a bunch of new missions. Oh, hey, Euclid launched now. I can move this up. Brilliant. We have fantastic outreach and education support. And I will skip back one slide to shamelessly promote Caltech IPAC has a new podcast web series that has just come out a few months ago called Explore Exoplanets: The Discoverers. I am the host, where I interview my esteemed colleagues who have discovered exoplanets about what it felt like and how they did it and what they found, what their favorite fictional planet is. And then I go into the NASA Exoplanet Archive and find the closest real world analog, and we talk about differences and similarities. So shameless promotion. Go check out the new podcast, or inflict it on your family and friends who are sick of hearing you talk about astronomy.
Like and subscribe.
Please smash that subscribe button. I know it's annoying, but the algorithm, guys, you live and die by the algorithm. If people aren't subscribed, the other people don't see it. And it's generally just a really great place to work. So I just wanted to explain to people what IPAC was. But let's talk about exoplanets. Okay. So we have, in March 2022, we hit 5,000 confirmed exoplanets. We're now at 5,500 and counting. But that's just numbers. What's cool about the planets that we found? These are all of the planets we've found using the transit technique, where the planet passes in front of the star and blocks some of the light. What I'm showing is the semi-major axis, the distance between the star and the planet, and the planet's mass, so the size of the planet relative to Earth. So Earth is at 1 Earth mass and 1 astronomical unit. So Earth would be here on that plot. And this is just raw numbers. This is a superset of all of the transiting planets that have been found. So you can't really do statistics with this, and you shouldn't. But there are already really interesting things you can see just from this plot. One is this cluster of planets up here. These are giant planets at very short periods. These are hot Jupiters. And one is this cluster of planets, this big cluster of planets down here, which are the warm super Earths and sub-Neptunes that Kepler mostly found. In between, you see this valley, this decrement. There's not as many things here. Now, this is a superset of many surveys, but it's harder to find these planets than these planets. So this is real. There's a real scientific, interesting thing happening between hot Jupiters and super Earths and sub-Neptunes. Something real is happening there. Now, where I showed you where Earth was, which is obviously an exciting place for many people, there's no detections. But that's not scientifically real. That's an observational bias. It's harder to find planets at longer orbital periods and smaller masses with the transit technique. So this isn't real, but this is real. These are all the planets that were discovered with radial velocity, still showing the same x-axis and y-axis. Radial velocity surveys have been going on for decades longer at this point than transit surveys. So actually we've pushed much further out from the star, which is super interesting. One thing that you'll see that's real on this, it's harder to find further out planets than inner planets. These are easier to find. And we've seen many more further out planets than inner planets. So this is real. There are really more cold giants than hot giants in terms of planets. Yeah. But this is not real. This is the same detection bias as before.
I went to CCA.
Okay. These are all the planets that have been found with microlensing. This is magic. A star with a planet lenses a background star. That background star suddenly gets bright. It's very cool. Importantly, we don't see that same detection bias with mass that we saw before, because it's not actually a function of mass like radial velocity and transits, where radius and mass are correlated. It's a function of the mass ratio between the star and the planet. So you can get very small planets as long as they're around very small stars, much more easily than for the transit and radial velocity technique. And what you can see here, this is actually a function of the selection bias of how far away the stars are towards the galactic bulge. So we're preferentially finding planets around what we call the snow line. So where things like water start to freeze out. And these are all the planets that have been found with direct imaging, which is what it says on the box. You use very exquisite instrumentation to block out the light from the star and look for nearby, usually hot young planets. So you can see, because it's directly imaging, the closer you are to the star, the harder it is to find. This is the opposite of all of the other techniques. The closer you are, the harder it is to find, because you're trying to block out the light from the star and look for planets. You need far away planets. And also, the larger the planet, the easier it is to find. This is the full picture, though. This is 5,500 planets. And we've covered 5 orders of magnitude in separation, 5 orders of magnitude in mass. There's a lot of really, really interesting stuff going on here, if only we can work out what's happening underneath. And that's what I'm excited about, not the numbers game. Numbers are cool. I love having more. But what can we use this huge population of planets to tell us about what's truly happening underneath? All of these detection techniques have biases, but we understand a lot of them. And once we know the underlying population, what does that tell us? What can we infer about planet formation, planet evolution, planet migration, right? How do we back this out into the physical mechanisms? Okay, that was just the intro. Overview of the talk. I'm going to talk about Kepler, which, as Megan said, I was in the Kepler Science Office for a few years, working on particularly Eta Earth, the frequency of Earth-like planets in the habitable zones of sun-like stars. Then I'm going to move on to K2 and TESS, which are extending Kepler results in many, many interesting ways. And finally, I'm going to come back to this picture that I just showed and talk about the challenge of producing this full self-consistent picture of planet formation and evolution across all of these orders of magnitude and separation and mass, and how we might rise to that occasion. Okay, take a breath. Let's talk about the Kepler mission. It launched in 2009. It was a 1-meter optical telescope. So this whole thing here was the size of like a small school van. It was designed, it had one main primary goal, which was to measure the frequency of Earth-like planets in the habitable zones of sun-like stars. One question. Now I almost went into Eminem rap then. That's okay. I stopped myself. It had one question to answer, which was Eta Earth. So it used the transit method, which is the method where you rely on the planet passing in front of the star and blocking some of the light. And it monitored 200,000 stars in this field of view on the sky for 4 years, mostly F, G, and K stars. This is the final planet candidate catalog out of Kepler. So now on this axis, it has the same direction as the previous one, but now I'm showing it in installation flux, how much flux that planet receives relative to Earth. So Earth is at 1. A planet here receives twice as much flux. And then on this axis, again, it's the same sense as before. Bigger planets are at the top, but now I'm showing planet radius. So Earth is here at 1. So this plus sign is Earth. And the rest of the circles are what Kepler found. They are colored by their reliability, which is how many times they passed the statistical tests that we ran to prove that it was a good candidate or not. So dark blue is super reliable, passed all of the tests all the time. Yellow is not very reliable, failed many of the tests. The contours are how good a job we could do at detecting those planets. So this was a huge suite of transit, injection, and recovery. So 0.3% of the time you would find these, and 0.01% of the time you would find these. That's not very much of the time, 0.01% of the time. And so hopefully what you take away from this plot is that Kepler didn't find any Earth-like planets, right? We have one unreliable-ish point kind of nearby, and the next closest points are already 25% bigger, which means they're 50% or more larger in mass. This one out here is really unreliable. Now that's a shame for a mission that was designed to determine this number, how common these are. And if you're interested, we could talk more about why we didn't hit that mark, but what can we do with what we have? We have this catalog, we have these contours, we have that reliability. What can we say? We can still make some statement. These are all of the different statements that have been made in the literature over the past 10 years or so on what this value might be, frequency of Earth-like planets in the habitable zones of sun-like stars. Now you can see for the first few years, before this final catalog came out, this 3 orders of magnitude in spread here of the potential for this number. People were guessing. People didn't have the completeness, and they didn't have the reliability, and they didn't have the final catalog. So you would just make assumptions and be like, I assume that above 10 sigma, we find everything. Turns out to not be true. So they were just guessing. Now, since we have the final catalog in the last 4 years and the final completeness and reliability, they have converged, which is kind of reassuring, but there's still a fairly large spread. I mean, these are 1 sigma uncertainties, so 0 and 100% are still allowed. But safe money is probably on somewhere between 10 and 50% of stars like the sun having a rocky planet like Earth in the habitable zone, with wildly large uncertainties and 1 sigma uncertainties. So we are still working on this, and there are still things we want to do with planet multiplicity, stellar multiplicity, rerunning the Kepler data to see if we can squeeze out any more completeness. So given that we have this number, 10 to 50%, why are we still working on it? Why do we care so much, and why do we need these error bars to be smaller? This is a plot from the Astro 2020 Decadal Survey, and it shows as a function of the size of a putative future space telescope in meters, 5 meters, 10 meters, how many Earth-like planets in the habitable zone of sun-like stars you might expect to find. And you can see this yield curve here. And the recommendation from the Decadal Survey was that if you had a 6-meter telescope, you could find 25 Earth-like planets, and you would need something like that to be able to do good numbers, right? Good number statistics. Now that was assuming an A to Earth of 0.24, which you might feel is safely within that 10% to 50% range, right? 24%. That's not so bad. The problem is around here, this curve is basically linear with the size. It goes as A to Earth to the 0.96. It's basically linear with A to Earth. So if A to Earth is 5 times smaller, which is 5%, which is absolutely allowed by the current numbers, then instead of 25 Earths, you're going to find 5 Earths. And now you have to start asking whether you want to spend $10 billion to find 5 Earths. So it's really important that we get this number right so that we build the right size telescope and then be able to find Earth-like planets. This is why I care so much about it. And we're still working on A to Earth. Now, so far, when I've talked about A to Earth, I've been talking about A to Earth kind of in absentia of other information. Just for a random sun-like star, what are the chances it has an Earth-like planet? But we have other information, and we have other correlations we can draw on. So I'm calling these conditional probabilities. What are the chances that this star has a rocky planet in the habitable zone, depending on what else we know about this star? And there's 2 in particular I want to highlight. There's one known correlation from Kepler called the peas in a pod correlation, which says that for a given multi-planet system in Kepler, the sizes of the planets are more likely to be similar to each other than different. If you draw 4 random planets from this population of Kepler candidates, the chances that they're always going to be near each other are low. And what we see is that many compact multi-planet systems have similar sizes, more similar than they would be if it was a random draw. Now that's really interesting because out here where Earth is, where we don't really get to with Kepler, we have found inner planets. We can find those. They're at shorter periods. They're easier to find. If we can identify stars that have closer in rocky planets, maybe that tells us something about the chances of there being a rocky planet further out. So rocky planets are down here, I should say. These are like sub-Neptunes. So if you've got a bunch of sub-Neptunes around your star, maybe you don't have an Earth in the habitable zone. But if you have a bunch of super Earths and Earths around your star, maybe you have a Earth in the habitable zone. So this is something that I'm really hoping that people push on in the next little while. And I was talking to Wenray about it this morning. I'm like, go make some predictions for me. Another one is how does A to Earth depend on outer planets? That was how does A to Earth depend on inner planets? This is a result from Marta Bryan from a few years ago. What she did was combine direct imaging and radial velocity results to show that 50 to 100% of systems with a gas giant out at Jupiter distances have an interior super Earth. Now that's super Earths, not Earths, but there's a whole debate right now about how important is it that we have a Jupiter, right? That we have a Jupiter in water delivery, in protection from asteroids. How important is it for life that there's a Jupiter? And then just in terms of correlations, if there are outer giant planets and that means there's inner smaller planets, that's great because we can find outer giant planets. I just showed you a whole bunch of them on that first plot. So how does A to Earth depend on other things we can measure between now and when Habitable Worlds Observatory launches? Habitable Worlds Observatory is what the Astro 2020 recommended flagship mission is now called. We have just actually started opening up the working groups last month. So if you're interested in contributing ideas or opinions to Habitable Worlds Observatory, the working groups are open right now. Please go check them out and join. Okay, that's Kepler, that's Ada Earth. Have a drink. So Kepler had that one specific question, right? Sun-like stars, habitable zones, Earth-like planets. So most of those 200,000 stars were selected to be, hopefully, sun-like stars. But there's a lot more stars in the galaxy than just sun-like stars. And we have two missions that came after Kepler, K2 and TESS, which are allowing us to really start exploring how planet occurrence rates change as a function of the stars. And this is super duper interesting. And so the next part is all results out of K2 and TESS over the last few years. I will point out one important thing. Kepler was a statistics mission. The funding and the project and the software were all set up to do statistics, and the data were made available for other people to do statistics with. TESS and K2 were not statistics missions. They weren't demographics missions. So the products that come out of those projects are not designed the same way. So we're starting from a much lower level in data with K2 and TESS than we are with Kepler. Okay, so let's talk about some of the cool results out of K2 and TESS. One of the interesting results out of the original Kepler planets have a bimodal distribution in size. So this is as a function of the planet size in Earth radii. So Earth is here at 1, the normalized distribution of short period planets less than 80 days. And what you see from Kepler, which is the pink dashed line, is that there's two peaks. It's not just a power law. Nature loves a power law. Everybody just expected it to be a power law, except for like 3 theorists who had predicted this. There's two peaks. There's a sub-Neptune peak and a super Earth peak. And in between, there's a valley. So one of the things we did with K2 was to look at K2 planet candidates. K2 looked at a completely different part of the sky. This is the Kepler field, and these are the K2 fields. It was an ecliptic plane survey. And this was work done by Kevin Hardegree-Ullman, who's a postdoc at the University of Arizona and is on the job market. And what he showed was that if you looked at K2, completely different data set, completely different analysis, you see the same bimodal distribution. So it's not some weird quirk of the Kepler field or the Kepler data. It's a ubiquitous feature of small planets across the sky. They're bimodally distributed. And then there was this really interesting result that I'm just tacking on because it's kind of cool. Before I get stuck with it. 2 seconds. Technical difficulties. This was a cool result. So for this bimodal distribution, this is in radius. And what these guys did would measure the masses of a bunch of these planets around M dwarfs and show that instead of a size distribution, it might be a composition distribution. These are isocontours in density. So this is Earth-like composition is the pink line, and a water-rich composition is the yellow line. And what they showed was that instead of size, maybe it's density, right? Maybe you have a bunch of rocky planets and then a bunch of water-rich planets. That's just around M dwarfs. So we don't know if it'll hold for the bigger stars, but that's a super cool interpretation of this. Okay, so this bimodal distribution, where might it come from? So there are a couple of theories in the literature that have become very prominent in the last few years to try and explain what causes this valley. One is core-powered mass loss and one is photoevaporation. They both posit that a planet starts with a large atmosphere and then something causes it to lose that atmosphere. Core-powered mass loss is the residual heat from formation of the planet pushing off the upper atmosphere, so you lose it. And photoevaporation is external high energy radiation from the star blowing off your upper atmosphere, so you lose it. And they both have some critical mass above which you have enough gravity to keep your atmosphere and below which you don't and you lose it, which kind of naturally carves out this valley. So these two very prominent theories have been kind of competing back and forth in the literature for a while. They were both kind of proposed to fit the Kepler data. So they both do a really good job of fitting the Kepler data. This is the Kepler data as a function of period and radius now. And one of the interesting things in the radius valley is that it's a function of period. So it actually, it's not there anymore, but it moves to a different radius the further out you get from the star. It shrinks down smaller and smaller. And actually both the mechanisms, core-powered mass loss and photoevaporation, predict that you'll see this. So there's not a really good way using the Kepler data to tell them apart. But there is one way, one space where they're very well separated, which is in the time it takes for them to happen. So photoevaporation is predicted to happen within the first 100 million years when the high energy radiation from the star is very strong. So this would say you're losing your atmosphere in the first 100 million years. Core-powered mass loss is a much, much longer, slower process and is predicted to be most efficient between 500 million years and 2 gigayears. So these are actually pretty well separated in time. So we need to look at planets as a function of time. This is a data point from just the field GK and M stars in the K2 data, and it's about 25% of stars have a sub-Neptune. So this is a planet between 1.8 and 4 times the size of Earth at a short period. So these are hot sub-Neptunes. That's these ones, hot sub-Neptunes. There's 20 to 25% of them once you get out to like 5 billion years. With TESS, you can see the uncertainties on this point, but with TESS looking at like 50-million-year-old clusters and finding a couple of planets, the occurrence rate is nearly 100%. Nearly 100% of stars in these young clusters that TESS looked at have a hot sub-Neptune, which is bonkers. It's just bananas that there's so many. But this is actually kind of not able to test between photoevaporation and core-powered mass loss yet. So what we need is a data point in here. Now, luckily enough, K2 observed 2 clusters, Praesepe and Hyades, that are 600 to 800 million years old, which happen right here. So the question is, if you look at Praesepe and Hyades, are there 100% or are there 25% or is there something in between? And there's 100%. So at 600 million years, you still have nearly 100% of stars having a hot sub-Neptune. So if the current timescales that have been published for photoevaporation and core-powered mass loss hold, it can't be photoevaporation, because 600 million years later, you still have all of these hot sub-Neptunes. They haven't all shrunk down to super Earths yet. That's if what is explaining this difference is something to do with evolution, right? Is explaining that the sub-Neptunes become super Earths. Other things could be happening. Other things include the fact that these clusters, which are much younger, are born at a different time in the galaxy, when the galaxy had a different dynamical history, a different radiation history. Planets in Praesepe and Hyades and these younger clusters might just be forming differently than the planets that formed 5 to 10 billion years ago. But if you assume it's some kind of evolution process, then this quite neatly fits in with the picture of core-powered mass loss. Okay, another cool result out of K2, so these are the K2 fields again. Some of the fields were in the galactic plane and some of the fields were out of the galactic plane. And this allows us to study the galactic distribution of planets as a function of galactic scale height. So this is a schematic of a cross-section of the galaxy. This is us, you are here. These are all of the K2 field pointings coming out from here. You can see the blue is the M dwarfs and the white is the FGK stars. So M dwarfs, you really can't probe outside of the thin disk. But with FGK stars, you are starting to get into the thick disk. So now we have super Earths, which is the lower hump in the bimodal distribution, and sub-Neptunes, which is the bigger hump in the distribution. And what you can see is that the function of the galactic oscillation amplitude, so this is how high a star gets above the galactic plane in parsecs, so 100 parsecs, 300 parsecs, 1,000 parsecs, what the occurrence rate of small short period planets is. So it's going from 30% down to like 15% or 30% down to 15% for sub-Neptunes. So this is showing that the higher you are as a star above the galactic plane, the higher you reach in your oscillation around the galactic plane, the fewer small planets you have at short periods. Something is being stamped on the population today that we see. Now, if you've thought about demographics before, then you probably know that there's a correlation between metallicity and planet occurrence rate. Stars with more heavy elements make more planets. And so we were like, okay, thick disk stars are more metal poor. Maybe they just have fewer planets. Maybe it's just the known metallicity correlation. But if you plot the known metallicity correlation, it looks like that. So the effect that we see is significantly stronger, statistically stronger than just a pure metallicity effect. So this kind of gets back to that question before of, is it a dynamical thing? Is it something about where stars are born in the galaxy and when stars are born in the galaxy? Adrian?
I realized we should have asked a question during
I don't mind.
You don't mind. Okay, then I have a question about oh yes, sorry. There's a strong iron abundance gradient radially in the disk, but not vertically, which is probably why that dashed red line is so shallow. But there's a very strong alpha abundance gradient.
Yes, so we are That's the next thing we're going to look at. I'm
Okay,
not actually
cool.
going to talk about it, but there is this really interesting thing with
I was just
metallicity,
gonna
and
ask, is there a correlation in planet occurrence with alpha abundance? I guess
there
that's-
does seem to be a strong correlation with alpha abundance and planet occurrence rate in prep.
Okay.
No plots to show yet. But yes, that's the next thing, is to think about alpha abundance, which is super cool. Okay, so there's a strong correlation between small planet occurrence rate and the maximum height above the galactic plane that a star reaches. What is that telling us about the planet dynamical history and the planet formation history? Why are these older stars that were born much earlier in the history of the galaxy making fewer planets? And this was work led by John Zink, who is a postdoc at Caltech and was working with me as a grad student. Okay, exploring the impact of stellar metallicity. So we were just talking about the fact that stars, planet occurrence rates are correlated with metallicity. So there's a known effect from Kepler and K2 that the more metal rich you are, the more planets you make. Now for giant planets, this is a very strong correlation. It's like this. But the smaller the planet, the weaker the correlation. So for super Earths, just believe what this is, for super Earths, it's still there, but it's much weaker. But there have been theories for a long time from people who do planet formation as to how metal poor can you go and still make planets, right? Like how much solid, what's the minimum solid material in the disk you need to just nucleate planetary cores and start building planets. And there were a lot of different predictions about where this would be, -1, -2, -0.5. This is in solar iron abundance. So Kepler and K2 didn't actually look at enough metal poor stars to push this all the way down, but we did this with TESS. The good thing about TESS, which is an all sky survey, so Kepler did 1 field, K2 did 19, TESS is doing the whole sky, is you have so many stars to play with. So what we did was take the 100,000 most metal poor stars from TESS and look for planets around them. If this metallicity correlation held down to between -0.5 and -1, we should have found 60 super Earths, and we found none. And we should have found them. Our detection efficiency was good enough. So there is really a very strong upper limit on the number of planets at low metallicities. Once you get below -0.5, we don't see any super Earths. We looked at 100,000 stars and we saw none. So this is actually a 5 sigma deviation from the trend continuing. If you said the null hypothesis was that the trend continues. And so this is a really interesting input now to planet formation theory. There's something that happens around -0.5 that starts to quench planet formation. And it's very, very difficult to make rocky planets below -0.5. And this is work led by Kirsten Bolly, who's a grad student at OSU, also on the job market. She's incredible. Look out for Kirsten. Okay, this is the last result from K2 and TESS that I'll show. So one of the known correlations from Kepler and K2 is that as you go to smaller stars, you make more planets, which is interesting, right? As you go to smaller stars, you make more small short period planets. And so this is a known result from Kepler and K2 from before, but there was a question of how long can this continue? Like how small can your protoplanetary disk be and still make planets? Like at some point, brown dwarfs would have 1,000 planets if this continued, right? So it has to not continue at some point. At some point, you don't have enough material to make disks. So the question was, how does this continue? Now, Kepler only had a few thousand, 3,000 M dwarfs, but K2 had 30,000. So we were able to push this further down and find that the turnover, I covered it up here, but I didn't cover it up here, and find that the turnover is just below 3,500 Kelvin, that you really do start to see as you go to smaller and smaller M dwarfs, you stop making these small short period planets. And it's just almost certainly some kind of reservoir effect, right? Like you don't have as much material in these disks around these very small stars. Now, the corollary to this is TRAPPIST-1. Have you guys met TRAPPIST-1? TRAPPIST-1 is a 3,000 Kelvin M dwarf that has 7 planets around it. So this is a challenge, but this is what we found with our K2 data. So those are some of the interesting results from Kepler, from K2 and TESS that are extending the Kepler results in really interesting directions. So have a drink. Let's come back to the bigger picture. All of those cool things that I talked about, I prefaced by saying small short period almost the whole time, right? Because that's what we can do with those surveys where we have enough numbers. But let's come back to this picture. Okay, Now, I talked about this picture and how promising it was. So many orders of magnitude in mass and so many orders of magnitude in semi-metroaxis. This picture is a lie. None of these techniques actually measure mass directly. The transit method measures radius, and I've used a mass-radius relationship to switch these all to mass. Radial velocity measures a minimum planet mass, so all of these blue points are really lower limits. Microlensing measures the mass ratio, and then you just have to make a guess at what the star is, and everything's an M dwarf, so they're all M dwarfs. Imaging, you're measuring the brightness of a blob, and then using some models to say, okay, if it's a 10 million-year-old star and it started this temperature, this is a planet that's 10 Jupiter masses. So there's a lot of work behind the scenes that we did to get this all in one plot. And that work includes assumptions and biases which might not hold. So that's line number one. Line number two is I make it look like this is all a coherent population, but there's a secret third axis coming out of the board, which is the types of stars that each of these techniques are looking at. So transits are doing nearby-ish FGKM stars out to a few thousand parsecs. Radial velocity is doing closer than that, much closer to tens of hundreds of parsecs, quiet FGK stars, right? So not just any FGK star, quiet FGK stars. And we just talked about photoevaporation, right? Like a way that the star's activity could imprint itself on the planet population. So the radial velocity targets might be different from the transit targets, and they might make different planetary systems around them. Microlensing is looking at very distant stars that are tens of thousands of parsecs away towards the center of the galaxy, and almost all low mass stars, so they're all M dwarfs. And then finally, direct imaging is looking at the very most nearby, tens of parsecs, young stars. So you want your directly imaged planets to be self-luminous so that they're brighter and you can see them, but that means they're young and they're hot. And I just showed you multiple different ways that planet populations can change with age. So there's no reason why these planets here would be there in 1 billion years or look like that in 1 billion years. So the plot is a lie, but it's so exciting because there's so much promise here. All of those things I talked about, we have ways to work with, right? We have ways to forward model these things. We have ways to model out populations. We have ways to try and extend the relations we know about how planets change as a function of stellar type and stellar metallicity and stellar mass. So I think that there's a real possibility here, and that what we need to do is build a planet demographics ladder. So people in the audience might be familiar with the cosmological distance ladder. So this is the fact that there are many ways to measure distances to things in the universe that work at different distances. There's a nearby method, intermediate method, very far method. And what we do is we calibrate those methods at the overlap regions. Like you're looking at Cepheids in nearby galaxies and that kind of stuff. So you calibrate at the overlap regions. That's the distance ladder. We need to do that for planets. So let's talk through what that might look like. This is an early radial velocity result. So from 15 years ago now, this is a function of semi-major axis. So Earth is here at 1, Jupiter's out here at 5. And this is the number of planets per star. And this is that early result that I showed you, which is that there are more cool giants than hot giants. That's the same result we saw in that first plot. But we knew that that couldn't continue, or direct imaging would be finding bazillions of planets out here at very, very far distances. And these were the upper limits from imaging surveys. So we knew that this had to turn over. So this is not like simultaneously fitting a population to 2 techniques, but it's using information from 2 techniques to infer something, right? This says it's going up, this says it has to be down by here, then we can say something about in between. This is bridging that distance. And then these were some early attempts to find that overturn. And then this was out of the California Legacy Survey from BJ Fulton a couple of years ago, showing that there is a turnover in the giant planet population as a function of distance. So there's not very many giant planets close in. There's a peak between 3 to 10 AU, and then it drops down again, consistent with those limits from direct imaging. That's pretty cool because our 2 giant planets are at 5 AU and 10 AU. So the peak of giant planet formation happens where we see our giant planets. That's great. Love to have a consistent picture. It's just one example of using two different techniques to infer something about the planet population. Now, there were previous techniques to try and do the exercise of simultaneously forward modeling a planet population through multiple detection techniques and their detection biases. So this is one from Christiansen and Scott Gowdy from a few years ago. So this is now log of period of the orbital period of the planet, so 1,000 days. And now this is log of mass in Earth masses, so Earth is here. So it's still distance and size. But what you can see is that mostly it's upper limits and lower limits and extrapolations. And this was just using earlier data sets that aren't as mature. But you can see some of the broad strokes that we've already talked about. You can see that planets get more common as you get further away from the star. You can see that there's more sub-Neptunes and super-Earths than there are giant planets. So there's some of these broad strokes. And this is taking a single planet population and forward modeling it through, it was radial velocity and microlensing and direct imaging. And this was just that the data sets weren't there yet. But the technique, I think, is good. Okay, so moving forward, what do we have to work with here? So this is back to this plot. I want to talk about the Nancy Grace Roman Space Telescope. So Roman is going to launch in less than 2 years, which is very exciting. And one of the things it will do is a survey of the galactic bulge. It's going to do a wide field survey, high cadence, many seasons, staring straight at the galactic bulge. The point of that survey is microlensing. And this is the kind of sensitivity, the expected sensitivity of that survey. Now, 2 things I want to point out. One is if you go out to where Earth is, the microlensing sensitivity is now sensitive to Earth-like planets. So I'm really excited about the possibility of folding in Roman occurrence rates with Kepler occurrence rates. Now, there is that hidden star axis that I told you about where, we've got to make sure that we can map the G stars to the K stars to the M stars. But Roman should be able to find Earth-like planets around G stars as well, just fewer of them. So one, super excited about A to Earth improvements, like 5 years from now. The other thing I want to point out is that for the giant planets, we're spanning 3 or 4 orders of magnitude in separation now. So if you want to talk about overlap regions where you can calibrate techniques, we're going to have overlap with direct imaging and radial velocity and transit. And so this might be some of the lattice work that we can use to kind of try and calibrate the populations from these techniques together. There's also Gaia. So the ESA Gaia mission is an astrometric mission. I haven't talked about astrometry yet because we haven't really seen a lot of astrometry planets, but we are expected to see many very soon. And this is kind of the population space that Gaia is expected to be sensitive to above this line. So again, I'm excited because it's a separate, completely independent technique, not looking at the galactic bulge, that will span multiple orders of magnitude in separation for the giant planets. So that's a separate check on this calibration, on building this ladder. So I think that's very exciting too. Okay, so that was a lot to cover and I probably went too fast. So I'm going to summarize. A to Earth, the frequency of Earth-like planets in habitable zones of sun-like stars, is somewhat constrained by the Kepler data. Not particularly well. 10 to 50% is probably safe money, but I wouldn't bet the house on it because it could be anywhere between 5 and 100%. But there are ways we can push this. So the Roman data, the conditional probabilities, reanalyzing the Kepler data, there's room for improvement and we're working on it because it's very high priority because Habitable Worlds Observatory really needs that one number. That number will set a bunch of architecture. Kepler was really looking at sun-like stars, but there are so many different planet evolution and formation and migration theories that depend on stellar properties that it's really exciting that now K2 and TESS are starting to open this field up, right? Like really start to push stellar metallicity, stellar birthplace, stellar age, stellar mass. All of these things are really starting to be accessible. And I'm hoping will be useful for the planet formation theorists in the room to start incorporating and moving forward with their theories. And finally, we do have an opportunity. There are so many planets across so many stars, across all of inner and outer solar system space that we have in our solar system, and across all of the massive things that we have in our solar system. There's a really exciting challenge to produce a self-consistent picture of the planets in our galaxy. It's going to be difficult because of the reasons I stated. There are lots of biases to correct and correlations to gently walk across to get to the bridge to the other technique. But I think it's really exciting, and I think the data are there, and I think we can do it. We just need to do it. So we should do it. And then finally, I'm just going to plug one more time. Go to YouTube, check out this new podcast. Tell me if you have questions about things that I can answer on the podcast, or tell me if you have questions about what I just talked about. Thank you so much.
All right, we have time for questions. Jessie, I'll let you call on people, but I'll be keeping an eye on Zoom. So if you're online and have a question, raise your virtual hand.
Leah?
Hi, super excited. I really love the NASA Exoplanet Archive. I use it all the time.
Thank you.
Have some stuff coming out with it. So I had a question about your plot with the core powered mass loss versus photoevaporation. I know a little bit more about the physics of photoevaporation than the core powered mass loss part.
This one or this one or this one?
Yes. Thanks. So I was wondering how you picked that threshold between like photoevaporation dominated and core powered mass loss dominated.
I read Hilke's papers and James's papers.
Okay.
And took the times that they said in their papers and put them on the plot.
So yeah, I'd love to talk to you after this because my postdoc George King has been showing for a few years now that basically that photoevaporation can still be pretty persistent and pretty strong out to a gigayear and more. And really the big uncertainty in that is the actual X-ray luminosity of the stars.
Yeah.
But the main reason for that is because the EUV just doesn't decay as fast as the X-ray does. So it actually can persist. But of course, like I said, like I don't think we've ever really plotted a planet like crossing the gap that late. But for that K2 planet, we might get close.
Okay. Yeah. So I tried to be careful when I was talking about this to say the current predictions, because I've talked with James and he's like, oh, we can make photoevaporation take longer. And I'm like, okay, well, sure, you can change any theory to fit the data once you have the data. So he and Hilke actually wrote a paper the week I was submitting this. It was such a neat story, guys, so neat. And then the week before I submitted the paper, Hilke and James published, these are the people who are the proponents of core powered mass loss and photoevaporation, published a paper together being like, maybe it's the other way around. Maybe core powered mass loss will happens first. And then because of the internal radiation puffing up the planet, it makes it easier for photoevaporation to strip it away. And I'm like, so there's a sentence in the paper which is like, alternatively, see recent work showing that maybe it's the other way around. So it's theories. They're working it out. I'm just trying to give them the data points, and they can work it out.
It's pretty messy.
And this is all assuming that this is because of evolution and not migration, right? Like maybe these get tidally disrupted. They're hot. They're within 10 days. It's very young. Maybe they go away because of migration. Like this is just if it's photoevaporation or core powered mass loss. Here are some data points for you. Caprice?
Great talk, first of all. I wanted to ask, hopefully it's not more of a solar system science question, but I think earlier in your talk, you talked about like inner Earth with like the outer planets, and 50 to like 100% have like Jupiter analog have an interior super Earth.
Yeah, this one.
So, and said that the importance of this like Jupiter analog is water delivery and asteroid protection, maybe from like forming the super Earth. So the question that I have is, there's like in our own solar system, do you know or do people know if Jupiter does this singularly by itself in our own solar system, because we have multiple gas giants and ice giants, and if multiple things like ice giants or gas giants would be just as important in other systems,
right,
as well.
So I'm not a solar system scientist, but I've read some of these. Everybody always talks about Jupiter. I think just in terms of the mass budget of the solar system, it's like 99% Sun, 1% Jupiter, rounding error, everything else. So I think Jupiter is the dominant thing out there, which is scattering stuff around. I honestly think it's still an open question, like Jupiter friend or foe, right? Like you know, the dinosaurs were extinct because a giant thing came from the outer solar system. Like, is Jupiter flinging stuff at us happily or badly? So clearly we survived with a Jupiter and we're here, but do we need a Jupiter to survive is the other question. And this is such an ongoing field, because even in the last 10 years, the consensus about whether the water was delivered from the outer solar system or not has changed. So we don't have a lot to work on to find stars that have Earth-like planets around them. So we're kind of grasping at straws. Anything we have, hey, if there's a Jupiter analog, let's look for an Earth. No worries. Henry?
Yeah, so at one point you were showing a plot for the occurrence rate of subneptunes for different stellar temperature.
Yep.
And you see a sharp cutoff sort of, and yeah, at 3,500 K. And is this for subneptunes only or small planets in general?
Give me 5 seconds and I will show you the, do I still have the screenshot that I saved it from? No, I cut this out of a screenshot that had more, I don't have it open anymore. So we have super Earth, sub-Neptunes, and then all small planets, and it's basically the same for all of them. There's a turnover, I think within the uncertainties, I think within the uncertainties, the turnover is about the same, maybe plus or minus 100. It's basically the same for the super Earths and sub-Neptunes. It's just less well constrained for the super Earths because we have fewer of them. So the uncertainties on the break are larger. I chose this one because it's pretty, but we also have super Earths.
Yeah, because I was just asking because if you think about TRAPPIST-1, those are Earth-mass planets.
Mm-hmm.
Sort of fitting this picture of not having super Earths or sub-Neptunes around stuff.
Yes, if the fact that they don't have super Earths means that there's room for Earths, great. But you know, I need folks like you, like Heismelders, who was originally the one who proposed that there would be a turnover, to go off and work out like what are the implications for lower mass things. I think Adrian was next.
Awesome talk. Really enjoyed it. Thank you. Next slide, I think.
This one?
Next slide, I think. It was the one showing occurrence rates versus. Next one.
This
The
one?
one from Kirsten Boley, sorry.
The one
Good.
before.
Oh, before, I see, yes. Good. Oh,
Yeah.
yeah, there it is. Metallicity, good.
Yes.
That's what I was so the binary fraction seems to go the other way. And there's no sharp features in it, in that lower
Binary stars.
Binary stars, yeah, sorry. Lower metallicity binary or stars seem to have a companion more likely than higher metallicity stars. There's no sharp features, so I don't think it'll explain this, but has anyone tried controlling for that in looking at planet occurrence?
So stellar multiplicity is a big deal, and no one ever does it right. So this is the 100,000 most metal poor stars in tests that have spectroscopic data and flags that indicate they're single.
Okay.
So
Yeah.
we tried.
Right.
This should be single stars. You know, I think the physics of star formation in the giant molecular cloud for low metallicity versus planet formation are not going to be quite the same. So we might not expect the same trend or the same types of steps. But there is certainly an underlying hidden issue of stellar multiplicity, which is never really well treated.
Right.
And is one of the things we want to try and fix for the Kepler data, because now that we have Gaia DR3, you know, go back, take out all of the binaries, try again.
Cool.
Yeah.
Yeah, thank you for the talk. Going back to the next slide, actually, occurrence rate of the subneptunes. I was wondering, so you take into account, especially to complete it with the sharp drop, the observational biases, right?
Yes. So this is after, you know, detection efficiency and reliability have been corrected for. This is what's left.
Okay. So yeah, I was wondering what kind of biases you take into account.
Yeah. So it's interesting as you get down to these. They're smaller, so the signal of a same size planet is larger, but they're noisier and fainter. So the reason this uncertainty is quite big is because we don't have a lot of planets around the late ends. The cooler you get, the fewer planets we have, and it's just an annoying signal to noise race to the bottom sort of thing. Daniel.
Thanks, super interesting. Back to the like core power mass loss photoevaporation, the like K2 field stars have
Yeah.
like no uncertainty relative on the fractional occurrence rate.
Right, that's because there's like 120,000 of them and there's 1,000 of these.
Well, yeah,
This is like putting everything in a bucket.
sweet.
And you can also, the subtlety here is this is GKM stars. The test analysis was separate. So these are slightly bigger stars on average. So I'm kind of mixing apples and oranges a bit here, which is why I tried to explicitly be like, they're not exactly the same stellar population, but this is the best we have. And Rachel Fernandez, who's working on the test data, is going back now to do more clusters. And the hope is that we can actually map this out more in time, because she had clusters from like 20 million years to 200 million years in her bin, which is why these are so broad. But the idea is to sample this more and to move to lower stars. But it's the same signal to noise race. The younger you get, the noisier it is, the harder it is to find things. Stars are difficult. Planets are so cool and stars are so hard. Any more questions? At the back?
I was just gonna ask, what of all the data that has now been collected on exoplanets, what have we learned about migration theory from any of this?
Yeah, so I was talking about this with the Planet Formation group before. So when I started this experiment in 2017, we knew from Kepler that this rate of hot sub-Neptunes was about 25%. But also the expectation is those hot sub-Neptunes aren't forming in situ, they're forming somewhere else and migrating in. So I actually thought I was going to be mapping out an increase in occurrence rate with time as these planets arrived, because either they're migrating through the disk, which is in the first 10 million years, and then they're already there, or they're migrating secularly over billions of years, and they're getting up to there, right? So when I was thinking of points in here, so we have Pleiades as well, which is like 165 million years. We have Upper Scorpius, which is like 5 million years. They're just, the younger you get, the more difficult they are to work with. But I thought I was going to map out migration. So then I got this number up here, and I actually put it down for a year because I was like, I don't know what happened. I did something wrong. This number is way too high. And then I started reading. The interesting thing is that the amount that this goes down by matches really well with the predictions that you lose 80% of them. And I was like, wait, that's the number. Maybe this is an evolution thing, not a migration thing. So to answer the question, I think one thing we can say is that these planets get there very soon, right? Like this is 10 million years, this is 100 million years, and there's already 100% of stars have a hot sub-Neptune. So if there's migration happening for the hot sub-Neptunes, it's happening quickly. So that implies something like disk-driven migration. They get there very soon. But I don't know that it stops. It might keep going, and that's what is happening here, right? Like maybe there's a reservoir of sub-Neptunes that's coming in, and I'm just catching a snapshot here. So the problem is I only have 3 points in time, and I have more than 3 theories. So anybody who hasn't done linear algebra in a while, I haven't constrained my problem. I need more data. So I'm back to the same place I was before. But the more data we get, the more interesting idea space opens up, I think. So I don't think we can say much about migration, except it's definitely happening quickly. If you believe that sub-Neptunes don't form in situ.